Welcome back. In this section, we're going to talk about collision. Unreal Engine has a sophisticated collision framework designed to accommodate the needs of a large number of game genres. In just about every game genre, you're always going to have to deal with collision in some way. The collision framework in Unreal Engine is a source of confusion for both newcomers and experienced developers alike. The aim of this section is to demystify the collision systems within Unreal Engine so that you can use them effectively in your games. This lecture will cover the fundamental concepts of the Unreal Engine collision framework. These are concepts that should be understood by all Unreal Engine developers. This lecture will cover the fundamental concepts of the Unreal Engine collision framework. These are concepts that should be understood by all Unreal Engine developers, from programmers to content creators. And every piece of information we'll be discussing here is important. If you take notes, this is a good lecture to take notes for. And you may want to come back to this lecture from time to time and give it another watch, once you've gotten some experience working with the concepts involved. So let's get started. In Unreal Engine, collision all starts with the primitive component. The primitive component class has the ability to have collision data. Primitive component is based on the scene component class, and scene components do not have collision data. Component types like static mesh component and shape component, things like sphere components, capsule components, etc., are based on the primitive component class. Therefore, they inherit the ability to have collision data. This ability is inherited from primitive component. When we speak of objects colliding or coming into contact with other objects, we are really speaking of primitive components. Static mesh components, sphere components, capsule components, these are all classes derived from primitive component. Therefore, they have collision, etc. All actors have at least one component, the root component. When you speak of collision of one actor with another, you should really be more specific and speak of the collision of specific components, because an actor can have more than one component with collision data, or none at all. An actor may not have any collision. Now, when we speak of collisions, we're talking about object geometries colliding or intersecting with each other. Two objects may be moving towards each other in the game, and at some point they meet, generating a collision. There exists another concept in the collision framework, the concept of queries. Queries involve checking the environment to see if collisions would occur. Examples are a line trace. This is when we cast a ray into space to see if it would hit something. Objects have to have their collision settings configured properly to be able to register a hit by a line trace. Similar to line traces, we have shape sweeps, also called shape traces, where we sweep a shape across space, a sphere or a box, for example, and see if that invisible shape would hit something, much like a line trace. We also have overlap queries. These are checking for overlaps with some invisible shape. So both collisions and queries play a role in the collision framework. Part of your responsibility as a game developer is to manage the collision data for objects in your game. Collision data consists of two parts: collision geometry and collision settings. Collision geometry comes in several forms. A static mesh has geometry in the form of its complex mesh. This is made up of triangles, and this is the mesh that you see when you look at the mesh in the game. We refer to this as its complex geometry. Static meshes can also have simpler collision shapes that are invisible. We often refer to these as convex hulls or collision hulls, or simply the simple geometry. We prefer to use these for collisions over the complex mesh because it requires simpler calculations and is more performant. Other types of components can be used for collision, such as shape components. These are things like sphere components, box components, capsule components, etc. But collision can take other forms in the engine, such as foliage, landscapes, and physics assets, a type of asset we'll learn about later on, so it's important to keep in mind that this is not an exhaustive list. Now, the collision settings determine how the collision geometry will be treated by the engine. This determines which types of calculations will be used for collisions with this geometry. Unreal Engine has a physics system and a query system. These are two different types of calculations that can be performed on collision geometry. So the first of the collision settings we'll talk about is the collision-enabled setting. When we think of collision-enabled, we think of what this component is used for. Is it just a visual prop? Does it need to interact with the world, etc.? Unreal Engine has a query system and a physics system, as we've mentioned previously. Collision-enabled dictates whether we use physics or queries, or both, or neither. The first option for collision-enabled is no collision. This is perhaps the easiest to understand. The object will not be involved in any collision calculations. Next, we have query only, no physics collision. A component using this collision-enabled setting only uses the query system. It is not involved in any physics calculations. Objects with query only can be involved with spatial queries. These are things like overlaps, traces, and sweeps. An object with query only cannot simulate physics. So physics collisions are not possible, and we cannot apply things like forces to the object. Next, we have physics only, no query collision. Components using this setting only use the physics system. So we detect collisions as a result of physics. When using physics, objects are moved around with forces. And when physics collisions happen, forces are what keep those objects from overlapping. Next, we have collision-enabled query and physics. This uses both the query system and the physics system. So a component using this setting can be involved in physics collisions, which the physics system calculates, as well as queries, which the query system calculates. It's the best of both worlds, but is also more expensive as it requires more calculations. Next, we have probe only, contact data, no query or physics collision. Objects using probe only do not get forces as a result of collisions. So even though they are involved in the physics system when it comes to calculations, forces will not be imparted on the object. However, these objects can detect collisions as a result of physics to execute things like hit callbacks on component hit, for example. So we register the collision, but do not have forces applied as a result. Objects using probe only do not use the query system. So no spatial queries such as overlaps, traces, or sweeps. And finally, we have query and probe, query collision and contact data, no physics collision. So objects use the query system and do not impart forces as a result of collisions. However, we can detect collision data as a result of physics executing those hit callbacks. So the setting we choose for collision enabled is very important because it determines the types of calculations performed on the component in question. And this can be impactful on the performance of our game, so it's important that our objects only use what's necessary. And we'll get practice using these. The next collision setting is the collision object type. This is a collision channel that represents the type of object from a collision standpoint. Unreal Engine has two different types of collision channels, trace channels and object channels. Trace channels are meant to be used with traces, like line traces and shape sweeps, and object channels are meant to be used with objects. An object, meaning a primitive component, cannot be assigned a trace channel as its object type. Collision interactions require us to be able to differentiate between objects based on their collision object type. The two types of collision channels are trace channels, which cannot be assigned to objects, and object channels, which are meant to be assigned to objects. The engine has a number of built-in collision channels, world static, world dynamic, etc. We can, however, create our own custom collision channels. But keep in mind that you can only create a limited number of collision channels. And it's best not to create too many, because each time we create a new collision channel, every single object with collision must decide how to respond to that collision channel. Because responding to a collision channel is a concept tied into the next collision setting, collision responses. Every object with collision has collision responses. These determine how this object responds to each collision channel. The responses can be ignore, which means there will be no collision interaction, and no collision callbacks called as a result, and we'll talk about callbacks more in a second. Overlap, in which objects pass through each other and can trigger overlap callbacks, and block, in which objects did not pass through each other, provided that they're both simulating physics or they're being moved via sweeping. And we'll talk about sweeping in just a moment as well. Blocking interactions can trigger hit callbacks, such as on-component hit, etc. So we've talked about the three collision settings. These collision settings make up a component's collision profile. Collision enabled, collision object type, and collision responses are what comprise this collision profile. And these profiles can be saved as named presets. Components that have collision have their own collision presets property. This is where we find the collision settings. You can select a preset here where the whole collision profile is filled in. Notice that when you select a collision preset, all of the collision settings are grayed out. You can't change these because the collision preset determines what these settings should be. Unreal Engine has a number of built-in collision presets. So if one of these presets fit the bill for your needs, you can use those for any given component that has collision. But you can also create custom collision presets. The engine does not limit you on the number of presets you can create, unlike collision channels. And it's encouraged to create collision presets rather than a large number of collision channels. These are great because you can easily set up a profile and apply it to a large number of objects. For instance, all of the walls in your level should probably have the same collision settings, so you can make a wall collision preset and apply it to all the walls in your level, and they'll all have the same collision settings. Now, rather than using a preset, you can set collision presets to custom, where all of these settings are no longer grayed out, and you can pick and choose each individual setting. The collision profiles for components that have collision are what determine the types of interactions they will have with other objects that have collision data. This determination is made using collision filtering, which is how we determine the types of interactions between objects. When two objects meet, we look at their collision object types and their collision responses. One object will have a collision response to the object type of another, but that other object will have a response to the collision object type of the first object. In the event that these responses are not the same, we choose the least blocking interaction. Ignore is less blocking than overlap, and overlap is less blocking than block. This is explained perhaps best with an example. Let's say we have two objects, object A and object B. And here's a simplified form of their collision object type and responses. Object A has collision object type pawn, and object B has collision object type world static. Keep in mind that object type is not the same as an object's class or data type. This is the collision object type, only used by the collision system. Now, object A's responses are block for world static and ignore for pawn, which means when object A comes into contact with another object whose object type is world static, object A's collision responses are as follows: block for world static and ignore for pawn. Object B has collision object type world static, and its responses are as follows: block for world static and overlap for pawn. So when object A and object B meet, we look at A's response to B's collision object type. Object A's collision response to object B's type is block, because B is world static and A's response to world static is block. Now we look at object B's response to object A's object type. Object A has the type pawn, and B has overlap against pawn. So B has an overlap response to A. So we have two conflicting responses, block and overlap. So we choose the least blocking of these two interactions. which is overlap. So the resulting collision interaction between object A and object B is overlap. Let's look at another example. We have object C and object D, and here is a simplified version of their collision profiles. So when object C and object D meet, we first look at object C's response to object D's collision object type. D is world static, and C has the response of block against world static. So C's collision response to D is block. Next, we look at D's response to C's collision object type. C has collision object type pawn, and D has a block response to pawn. So D's collision response to C is block. These are both block, so the resulting collision interaction is a block. Note that this is the only way that we get a blocking collision interaction. Both objects have to block each other's collision object types. If just one of them has a less blocking interaction, such as ignore or overlap, we will not get a block. So the most important line from this slide is this one. We always choose the least blocking interaction. Ignore is less blocking than overlap, and overlap is less blocking than block. Now, collision interactions can result in collision callbacks. These are executed in response to registered collision interactions. Overlap callbacks, such as onComponent begin overlap, actor begin overlap, etc., are executed in response to an overlap interaction. Both objects have to have their generate overlap events property set to true. This is a checkbox in the details panel for that component. We also have hit callbacks, such as onComponent hit, and these are executed in response to a blocking interaction or a probe. Now, if this is a physics collision, then hit callbacks will only be executed if the component generating the hit event has its simulation generates hit events set to true. However, if it's a non-physics collision, then this collision must be the result of sweeping movement. And we'll learn about what sweeping movement is, but if an object is not moved with sweeping, it will not have a hit callback executed, as there will not be a blocking interaction. So now that we know how to determine what type of collision interaction should result from two objects meeting based on their collision profiles, the actual outcome that we will see in the game depends on the method of movement. You see, two objects can come into contact with each other because they were moving. The way that those components are moving matters. Now we have three main ways to move an object. First, we can move an object directly by setting its location, using functions like setActorLocation and addActorWorldOffset, and these types of functions have the option for sweeping or no sweeping. Sweeping involves stopping an object if it encounters a blocking geometry between its old location and the new location that we're setting for it. Without sweeping, we could place two objects in the same location, overlapping each other, even if they're set to block each other's object types. But with sweeping, blocking objects will not overlap because the sweep will stop them from doing so. And this uses the query system to calculate and detect and prevent that overlap. The function addActorWorldOffset, for example, has this sweep parameter. It's a simple Boolean input, and without this checkbox checked, we will not have sweeping, preventing two blocking objects from overlapping, at least with the query system. Now, objects can also be moved via the physics system. Objects simulating physics are moved with forces. So we can move objects with functions that add forces, such as addForce. Once we add force to a component, we then leave it up to the physics system to handle moving that object. And finally, we have movement components, and these are more sophisticated ways to move objects. We've seen the projectile movement component. This movement component has the ability to move an object, whether it's simulating physics or not. The movement component checks to see if physics is enabled on that object. If it is, it launches the object, just like adding a force, and then leaves it up to the physics system to handle how that object moves or flies through the air. If the object is not simulating physics, then by default, the movement component moves the object by updating its location using sweeping. So then the object can be blocked using the query system, for instance. But movement components are highly configurable, and you can disable sweeping on the movement component and just have it update its component's location without sweeping. We also have the character movement component. This is used for moving characters, which we'll get some practice later on in the course with. Character movement components move their character's root component by updating its location and using the query system. This involves using sweeps to stop the character from passing through blocking objects. But it's also simulating physics, and it will impart forces on objects that are simulating physics. So it uses both the query system and the physics system, and as we've learned, this is more expensive than just one or the other. So the collision framework in Unreal Engine is complex, as we've just seen, and the easiest way to learn about the system is hands-on. We will need to see various examples of collision data and collision settings, as well as various methods of movement, to gain some understanding of what to expect when objects register various types of collision interactions. So I've created a collision examples project. This is going to be in the resources for this video, and this is going to allow us to see the results of various types of collision interactions using different objects that are moved with different methods of movement, and we'll be able to see different collision settings and observe the results of those interactions. Well, the collision system may seem daunting and complex at first glance. After this section, after you've gotten some experience with the various types of collision interactions, it's not going to seem very complex at all. And I do recommend that you come back to this video at the end of this section at the very least, and watch this video one more time and see just how many concepts make more sense to you the second time around. So I hope you're ready for some collision interactions. I'll see you in the next video.